Right. Okay, recording has started, so we can get going. So again, welcome to our Ask an Expert session. My name is Steve. I will be your moderator, and this is our monthly Ask an Expert session. And this month it's a little special. We're doing something a little bit more complex, and we're going to be talking about external memory interfaces with experts from our Interconnect and Memory Interfaces application group, Bhumika and Damaris. So I want to introduce our experts. So this month you get 2 experts for the price of 1. We only advertised 1 expert, but we got 2 to come and talk to us about external memory interfaces today. So Bhumika has been with Intel for 15 years. She's been in hardware validation. She was in hardware validation product engineering for 7 years and in the customer experience group factory apps group for 8 years. She's worked on internal memory blocks, SoC, and the EMIF IPs. And these days she's focusing on DDR4, HBM2E, and Optane. Your other expert today is Damaris Renteria. She graduated in 2019 from University of Texas at El Paso, and she's been in our emerging professional rotation program for 2 years before she settled into the Interconnect and Memory Interfaces applications team. She's been focusing on collateral development, IP checkout, reference design creation, and customer support. So those are your experts for today, who you will hear shortly. So why you're here, you want to learn about the newest DDR memory protocol, DDR5. We're going to be focusing on that, and our experts will give you an overview of the technology. You're curious about the differences between DDR5 and previous protocols. They will be going into a discussion about the differences between DDR5 and DDR4. You want to know about what FPGAs are coming that will support DDR5, and maybe you have other questions about memory and the memory interface IP. So how is this going to work? So if you have not attended one of our Ask an Expert sessions previously, it's very simple. I'm your moderator. If you have any question at any time during the presentation or during the question session, you have 2 options for asking. You can either simply unmute yourself and ask the question, or put something in the chat. I will be actively monitoring the chat while the experts are focusing on the presentation, and I will relay it and get their answer to your questions. So please feel free to ask your questions at any time. The ground rules for your questions. So any question you can think of about memory technology or the external memory interface IP is fair game, over the phone or in the chat. If it's a detailed design-specific question, we'll try to answer based on what information you provide. Hopefully, your questions can be answered in a reasonable amount of time because we want to get as many questions in from as many folks as possible. So if you have a question, we'll do what we can. If the question cannot be answered to your satisfaction, we may point you to your local FAE, and they should be able to help you out with more information. So with that out of the way, and without further ado, I'm going to hand it over to Damaris and welcome her and get into our discussion about DDR5. Damaris?
Hi, everyone. Welcome. So today I'll be going through a DDR5 technology introduction, as Steve mentioned, and just a quick of what DDR5 stands for. It's a double data rate, and this memory protocol is the next stage in the evolution of the double data rate RAM technology. So next slide for the agenda. I am going to talk about or introduce DDR5, which is introducing the new features and changes from the previous standards. As well as in the second part of this presentation, I'll be comparing DDR5 to its predecessor DDR4. And more specifically, I'll be highlighting some key performances such as throughput, the pinout description, mode registers, and some popular commands. And please note that this presentation focuses on DDR5 technology in general, where most of the content is based on the DDR5 JEDEC spec. So not all of these features mentioned will be implemented in our Intel Agilex N-series devices. Next slide. So for DDR5 introduction, we're going to start talking about the evolution of signal data rate and DDR standards. So the first main point to notice from this table is that there's a significant increase in speed performance from the signal data rate to DDR5 standard. So where for DDR5 we can achieve a maximum of 6,400 mega transfer per second. And with a theoretical speed of 51.2 gigabytes per second. The DDR5 standard with the speed can provide a significant performance boost over the previous versions, as well as we can see here the voltage row that for DDR5 memory, it's reduced from 1.2 to 1.1 volts, which improves the power saving efficiency by 8, or this is what is mentioned in a vendor analysis. So this can reduce system power consumption and heat generation, especially for industry systems that require low power consumption and have difficulty with heat dissipation. And of course, lastly, you can notice that the prefetch is double to what DDR4 and DDR3 had. So instead of 8N, we have now 16. And moving on to the next slide to introduce more about DDR5 memory. We are going to talk about how the DDR5 memory was developed with the new channel architecture. So it now provides two sets of completely independent 32-bit subchannels. So not only does the double bandwidth mode improve overall performance, but it also effectively shortens access latency and improves channel efficiency. And of course, when ECC is enabled, you get a 40 bits per subchannel as shown in the diagram on the side. Apart from that, we have for DDR5, we have a burst length or burst chop that was extended to 16 for the burst length and 8 for the burst chop to increase burst payload. So burst length of 16 allows a single burst to access 64 bytes of data, which is typically about a CPU cache line size. And it can do this by using only one of the two independent channels, so only half of the DIMM. This provides a significant improvement in concurrency. And then there's also a third option, the BL32, which is available only for by4 configured devices for systems that utilize the 128 bytes cache line size. And this feature will generally just further improve the efficiency. And continuing on with the next
question in the chat, Damaris. Was DDR4 36 bits per channel, 72 total?
Yes, 72 total. That's correct. With ECC enabled, that would be.
Slide. Sorry.
And here for the bank groups of DDR4 memory, it has increased. So it was 4 in DDR. It was 4 bank groups for DDR4, and now it's 8. And the total number of banks has also increased from 16 to 32. So however, the number of banks per bank group is still the same. So we still have 4 banks in each bank group. And the number of bank groups were doubled, which helps to increase the device density and the amount of data transmitted, as well as allows more pages to be open at any given time. So thereby optimizing the overall system efficiency. And another benefit of having more bank groups is that the bank group to bank group interleave timing access are shorter than the bank to bank within a specific bank group access, as shown in the quick diagram below. So this enables controllers to avoid performance degradations associated with sequential memory access within the same bank. And going on to the next slide. So other features added to the DDR5 module are a high precision temperature sensor. So this provides detailed memory temperature data to monitor the heat dissipation of the memory in real time. We also have a serial precedence detect, or the SPD hub, which allows us isolation of a local bus from a master host bus. So in this case, our local bus would be the sideband bus, where the sideband bus is used to address the limitation of I2C used for host access to DRAM DIMM resources. So here as a side note, the sideband bus default is I2C, but you can switch to I3C mode to operate at a max rate of 12.5 megahertz. And lastly, another feature added was the power management IC, which can control the power load more efficiently and improves the power conversion efficiency. However, instead of like in previous versions, it was controlled by the motherboard, it's now being added into the actual DRAM memory. And next slide. We're continuing on additional features. We do have an on-die ECC or error correction code mechanism, which can automatically detect and correct data errors in the memory. This provides an end-to-end complete protection for the data transmission process and improves memory data fault tolerance, so thereby improving the overall data accuracy. An additional feature to the ECC mechanism is the error check and scrub, which reads internal data and writes back corrected data if an error does occur. Next, we have DCA, or the duty cycle adjustment, which adjusts both the DQ and DQS duty cycle distortion. So this feature was introduced due to the increase in memory speed for DDR5. And for the cycle redundancy check, or CRC, this is not a new feature. It was previously in DDR4, but it did not support write operations. So for DDR5 CRC, we are now supporting both the write and read operations. And basically what CRC is used for is to detect errors in the digital data. And lastly, the multi-purpose command, MPC, it performs functions like the interface initialization, training, and periodic training. So on previous DDR DRAMs, these functions were individual commands or they were mode registers settings. So now they're just in one command. And next slide, please. So the new refresh feature that we have in DDR5 is a refresh that can occur, or a refresh that's called same bank. So in DDR5 memory, this allows the system to update a specific bank without affecting the access of other bank data. So it greatly reduces overall idle delay and improves the system performance. And basically in previous double data rate standards, for a refresh to occur, all banks needed to be in an idle state and cannot execute any other instructions at the same time. So this is a new feature added, which is going to be helpful. The only thing would be is the target bank would be inaccessible during the same bank refresh cycle time. Though banks will have, other banks in each bank group are accessible. And for the refresh management, this improves or protects the integrity of DRAM data, same as what we had in the previous generation with the TRR, or the target row refresh. But however, the refresh management additionally improves the low latency, and as well, the controller does not have to track the individual target row as it does in the target row refresh. And just the background, so the target row refresh is a protection mechanism. So this will refresh the victim row affected due to the hammering impact from the neighboring bits. Next slide. So for the DDR4 DIMM keying, an important thing to keep in mind is that the notch is in the center of the module, and this notch acts like a key used to prevent unsupported modules from being installed. And for the UDIMM and LDIMMs or RDIMMs, they do have different notches positions for DDR5. So please be aware of that you cannot use or replace so easily a UDIMM with an LDIMM. for DDR5 module. And for more information for the DIMMs on the next slide, we have that the DDR5U Dim have a significant different pinouts compared for the DDR5L and R DIMMs. So as well as the notch, please keep aware of this different pinouts. And basically for the UDIMMs, you have two sets of single data rate command and address bus. So there's no register clock driver and there's no PAR pin on the DIMM connector. And for the L DIMM and R DIMMs, we have two sets of double data rate for the command address bus. And for this one, we do have a register clock driver, which is basically, it can further reduce the load of the CPU. And same as the UDIMM, no different. So we do have a PAR on the DIMM connector, and it's the input to RCD01. And note that the PAR does not go to DDR5 devices because there's no PAR or parity pin in the DDR5 module. And on the side, this picture is only for the UDIMM. I did not have the LDIMM or RDIMM front view schematic to show, but you can find these in the datasheet. For the next slide, it's going to be the DDR5 standard specification. It's just a summary of what I've mentioned before. And so just a quick overview. We do have, I did not talk about the equalization, which is DFE or dynamic feedback equalization. And basically this one, due to the speed increase to 3,200 megatransfer per second, there were some challenges in the DQI openings. So therefore, this new dynamic feedback equalization was introduced for the DDR5 standard. Apart from that, everything else is just summarized. And so for the number of banks, when you have an 8 GB in a by 4 by 8 interface, DQ interface, you need a 16 bank or 8 bank group with 2 banks per bank group. And for a 16 through 64 gigabyte interface, or with a by 4 and by 8 DQ pin, you'll need it'll double the size, so you'll need a 32 bank with 8 bank groups and by 4 and 4 banks per bank group. And you can see this in the core architecture with the number of banks. And when you have only 4 bank groups, that's only with the 8 gigabit, you'll need 8 banks, 4 bank groups, and it will be just 2 banks per bank group. It will be the same as when you have it for the we say for this will be only for the by 16, so there's no by 4 and by 8 with the 4 bank group. And this would be it for the DDR5 standard specification. So moving on with the DDR4 versus DDR5 standards. So mainly we can see here in the throughput, we can see here that the DDR5 throughput starts from 3,200 mega transfers per second to 66,400 mega transfers per second. And according to the JEDEC spec, the DDR5 memory will ultimately scale to a data rate of 8,400 mega transfers per second. We can also see that the clock rate varies from 1,600 megahertz to 3,200 megahertz, corresponding to the speed bin above. As well, for the DDR5 memory, we can see that the CAS read latency varies from 24 to 56 clock cycles, and unlike the DDR4 standard, DDR5 CAS write latency will always equal to the CAS read latency minus 2 clock cycles. And the DDR5 will also include more preamble and post-amble settings so that it can handle higher frequencies. We need to actually accept the we need to accept the write preamble and post-amble correctly to make sure that the DDR5 can receive and send the data properly according to the selected spin bin. DDR5 also supports 2N mode to provide more setup and hold time in the command and address bus. And so I mentioned burst length of 16, which allows the user to access more data per each request. And the DFE or decision feedback collection is available, as mentioned earlier, for DDR5 memory. So that would be for throughput, and continuing on with the pinouts on the next slide. So here, mostly all the pinouts between the DDR4 and DDR5 protocol are identical, such as the differential clock inputs, the chip select, the reset, and the alert pins. However, for the data mask inverted signal, DVIN, this one, DIMM pins are not available, or data bus inversions are not available for DDR5 devices. They are only DIMM. And then for all the command address bus signals, like the ACT, the band groups, and the separate TAN, they were all combined into this single 14-bit bus, the command and address CA bus in DDR5. So they're no longer separate. They're all just one multiplex 14-bit command address bus. That's going to be changing. And then apart from that, everything else the same except for the mirror. So there's a new pin called mirror, which informs the device that certain pins are swapped. It also improves the disorder for DIMMs that have devices in front and on back sides. We also have the CAI pin, which is a command and address inversion that informs the device if any command and address pins are inverted. And lastly, we have the DBDQ and DBDQS pins, which they are calibration pins, and they stand for loopback data and loopback data strobe. And these are the output of the selected DFE or the decision feedback equalization phase, and this is used for testing purposes. And that would be the main differences. And continue on with mode registers and commands. So as mentioned in these earlier in the DDR5 spec statement, we are using 2 cycle commands. So basically, these commands are sent to the memory command and address bus, and each command can be a 1N mode or a 2N mode, where the 2N mode allows signal to provide more setup and hold time on the command and address bus. And 2N mode is enabled by default. So on the bottom, there's an example for the right pattern. It's a 2-cycle command. And the MPC, the multi-purpose command, is a 1-cycle command. And we can notice if it's a 1-cycle or 2-cycle command by the CA1, which is the purple, the broke highlighted in purple. So if it's a 0, it's a 2-cycle command. And if it's a 1, it's a 1-cycle command. That's how we will be able to identify these commands. Moving on to one of my final slides, which is the key takeaways. So for DDR5 architecture, the DDR5 architecture provides higher capacity and higher throughput and more flexible configurations. It also integrates the built-in DFE and trainings to enhance signal integrity and calibration. And as well as the commands are sent through the command and address bus, where 1 or 2 cycles is the 1N mode and 2 to 4 cycles is the 2N mode. And also just another note I did not add here is that the motherboards typically only support DDR4 or DDR5, but they do not support both modules. And then lastly, I added another slide at the end, which is supported features. So in this table, I tried to compare the generic DDR5 features versus the DDR5 features that we're planning to use currently with our Agilex M series devices. So as I said, this is what we're planning currently. So this might change by the next Cortex release, which is 22.4. But as right now, we are supporting only component density of 16 gigabits and the speed bin up to 5,600. Oh, and then a quick note. So when I say that ECC is only sideband on our Agilex EMIF supported features, that I forgot to add a asterisk, but this is ECC sideband is the regular ECC that we enable by the controller. So this is supported or configured by the controller, and on that ECC is just it's transparent to the controller, so the controller does not have to do anything with it. So that's why it's kind of faded out, but it is available. So this doesn't change regardless of your memory configuration or anything. It doesn't affect it on your on-die ECC. And that would be all on my part.
Okay, great. Just to, so did you want to mention these resources too before we get into the Q&A?
Yeah, I can mention. So for any information for documentation or for any of our debug tools, you can go to the EMIF-IP Support Center. And I think Steve is going to put these links in the chat. And then as well, there is a white paper for our Agilex M series devices, if you're interested in learning more about what is going to come with this device. And as well as a link to the JEDEC standard for DDR5, which is where most of this information is coming from.
And I've also, so I just put the links to all that in the chat. I also put a very custom link to our available online training. Right now, our existing online training covers Stratix 10 and current Agilex devices. Of course, as we move into DDR5, we will be adding and updating existing training to provide more detail on that support. And I put a link to our training catalog in the chat on that. All right, so I haven't seen too many questions in the chat, just a couple so far. Just to reiterate what we got so far, it was asked, what was DDR4 36 bits per channel, 72 total? And Damaris, you mentioned that yes, that was the case with ECC, right?
Correct.
Okay. There was another question that was asked and Bhumika answered in the chat, but I'll reiterate it here. 2 channels with DDR5 only apply when using DIMMs, not when using discrete components. And Bhumika said that that was correct. Your channel concept is only for DIMMs. I don't know if Bhumika or Damaris, you wanted to expand on that at all?
Yeah, so I can extend on that. So for discrete modules or component interface, your interface width for DDR5 will be limited to by 32 or by 40 with ECC. And when you move to DIMM, you can get up to by 80 with 2 channel concept. So each channel will be by 40 with ECC, and without ECC, it will be 72-bit.
Great, thank you. Another question just went into the chat, which I think we kind of just answered. So not quite yet. I guess people are asking about when M series is coming. Is DDR5 controller available from Intel, and if there's any documentation available for that? And I'm pretty sure the answer to that is not yet, but you both can probably expand on that.
So our Agilex M series will be supporting DDR5. And the documentation or any further information on that device as well as DDR5 will be available by end of this year.
Okay. So I have a few other questions that were asked before the session, but again, if there is anybody in the session right now, if you have any questions, please feel free to put it in the chat or raise your hand and unmute your mic, and we can answer that right away. From the previously asked questions for the session, somebody was asking about general differences between DDR4 and 5. I guess that's really, we went into some specific things, but are there any more general high-level types of differences that people should be aware of when implementing a design between DDR4 and DDR5 that you both might want to comment on?
Yeah, I can start, and Bhumika, if you have something afterwards, feel free to add it on. So for DDR5 modules, it has a higher base speed, so it supports higher capacity DIMM modules. And it also consumes less power for the same performance specs as DDR4. However, for DDR4, it does have some key advantages against DDR5. So it, like the overall lower latency, and as well as it has a better stability. And as for like applications, I know some of them for you can use DDR5, which is mostly right now for videos and image editing, as well as for 3D tools and browsers. That's mainly what's been used for as right now. It might change as DDR5 grows in the years.
Yeah, there was another question about use cases, so I guess that kind of answers that one, unless there's other use cases that you wanted to bring up. For DDR5, that is.
So it will be helpful in data center and cloud computing as well, because you are seeing an increase in your bandwidth and performance, plus the low power helps there too.
Okay, there was also a question about comparing the bank groups between DDR4 and DDR5. Maybe I'll just jump back to that slide if you want to talk more comparison on bank groups.
Jimenez?
Yeah, so for DDR5, as mentioned, so it has 8 bank groups. So it is the double of what DDR4 had. It had 4 bank groups. And I guess the main takeaway for here on my part is that the interleave or the timing axis between back group and back group, it is shorter. I know that's kind of the main thing here to take away. So the timing axis is shorter for back group to back group versus the time axis between the actual banks inside the bank group. Apart from that, I don't know, Bhumika, do you want to add?
No, you capture the main key advantage that the timing associated with switching between banks is shorter compared to DDR4, and that saves the overall performance, right?
Anything else on bank groups? Because we have another question in the chat. We got a specific question to Agilex DDR4 usage. If you're using 2 controllers on the same side, DIMM2 and DIMM3 on the dev kit, are you aware of any pinout restrictions that occur when both controllers are instantiated, added to the design, versus when the FPGA design is compiled with only DIMM2 or DIMM3 instantiated? This person has a resource pinout compile error when they're compiled together, but not when they're compiled separate. They're sharing the calibration IP as required. Or are there any issues with using both DIMMs as opposed to only one at a time that are known?
So to give you a very specific answer, I need a little more detail, and you can reach out to Steven, and then Steven can help me reach out to you. In general, if you have 2 controller on the same side of the Agilex, right? There are restriction in terms of IO bank sharing. So if you look at our Agilex F series and I series um, architecture, you will see there are 96 IO pins, and the IO bank is divided into 2 sub IO groups of 48. So there is no sharing allowed within that 48. So if you have your 2 interface overlapping IO bank, you might run into some fitter issues. So as I said, I need to exactly see the pin placement, and then I can help you there. When you compile a design with a single instance of memory with the pinouts, it usually not flag the conflicts that are coming from the other interface placement.
It's the dev kit. It should be okay, right? Or
Yeah, it should be okay, but I need to just see how they have placed the pin. We have designs. If you can tell me which exact, it's a different pinout from the dev kit. Okay, okay. So I need to see the pinouts to make sure that there is no IO sub bank sharing is happening.
okay. I sent my email to that attendee. Thank you for your question. Oh, they're saying the data pins are what are causing the conflicts. Okay, well, we'll get more information about that offline. Another question that was asked from before the session, more detail on the Power Manager IC, the PMIC. I don't know if either of you want to talk a little bit more about that. You just kind of mentioned it in the list here, but maybe more detail about how that works and what it does.
Do you want to take the question?
For me, what I know about this is fairly new for me. I know it was in the motherboard and now it's in the actual DIMM, which what I know about is that's gonna make it better since you're gonna have be able to regulate the power, I guess, at real time. Apart from that, more specific.
Yeah, so you covered that part. So basically, it helps you regulate the power on the DIMM side rather than coming from the motherboard. That's the biggest advantage. So it saves the power as well as it provides the power when needed. So both things are handled through PMIC.
Okay. Another question that we got before the session. Should I start thinking about upgrading my design to use DDR5? So what are the situations where people should start thinking about this, or what?
So from DDR4 to DDR5 is so if you are trying to use the same board and same pinouts, it's not going to work, first of all, because the footprints are different for DDR4 and DDR5. But if your application needs a more bandwidth as well as the power saving, then moving to DDR5 is a better choice. But again, the cost is also associated with it. DDR5 DIMMs or discrete components are a little bit expensive compared to DDR4. So there is a performance power versus cost associated with it.
When do you think DDR5 is going to really be starting to take over as the standard?
So Intel's processor have DDR5 already. In terms of like external memory interface, right? Like what we do on our dev kits or with FPGA is still picking up. So probably within a year or two, you will see a market open up for DDR5.
Great. And one more prior question, the maximum density support for DDR5.
So as per information available from Samsung, their maximum capacity is 512 GB. So they are able to compact 512 GB worth of capacity into one DIMM. So that would be the maximum. And depending on what memory format you are going for, what is your base device capacity, as well as how many ranks you have on the DIMM, whether you have a 3DS versus non-3DS, that will also impact your maximum size of your DIMM capacity or interface capacity.
Okay. All right. That's all the previous questions I got. Are there any more questions from anybody in the session today? Get them into the chat. Oh, what is 3DS?
So 3DS is like a stacking technology. So let's say you have in non-3DS device, you have a single discrete component based device. Think of like a stacks of that single module within same package. So it's in package stacking. So you will have a like a depth of the memory increase within a package. So single layer, second layer, third layer. So most time if you see in RDIMM, LRDIMM technology, and this applies for DDR4 as well, you will see 2 high stacks and 4 high stacks. That means for a single discrete device footprint, you will get 2 times and 4 times of depth.
Okay. Are there any other questions? Again, please feel free to put in the chat, or you can unmute your mic and ask our experts. Still have some time left, but if we don't have any questions, we can end the session. But I'll give it a minute. Damaris, Bhumika, is there anything else that you wanted to bring up or mention, perhaps about Agilex M series that you can, or anything else you want to talk about with the EMIF IP, if there are changes or anything, improvements coming, or anything that you wanted to highlight while we're in the session here still?
I just want to mention that please stay tuned for Agilex M series information available. Is getting available in end of this year, so you will see more information coming in. But there is a white paper and there is a product launch presentation on Intel website. Please have a look at it. That will give you an overview of what Agilex M device would be and how you are seeing a performance benefit with Agilex M series.
Oh, we got another question in the chat. How many components can be connected to an Agilex M?
It depends on the floor plan, right? It depends on what device you are looking at and how many IO banks are available. But in general, and again, it depends on your size of your interface as well, right? So if I just roughly calculate by 32 interface for DDR5, you will get it by 8, almost 8 memory interfaces, but there are other restrictions that you will learn through upcoming documents.
Oh, another question. Can controllers be bonded to have an effective 128-bit or 256-bit wide interface? I presume that's with DDR5.
Yes, but there are restrictions. So as I said, please stay tuned for the documentation and you'll know more information there.
Okay. Any more questions coming in? Damaris, did you have anything else that you wanted to bring up or mention?
No, I don't think so. It may be for, I know for the future, like again, by the end of the year, we are gonna do that's one thing we forgot to add in the links of our floor plan, which is helpful for figuring out which interfaces can fit in what devices and specifically see it in a diagram instead of just running it through CordisFitter.
Is that in the interface planner, or is that going to be a different tool?
That's going to be a different tool. It's
okay.
The link is within our device selector tool, which is in our EMIF support center page.
Here, yes.
Yeah. So if you go there and if you go into you download our device selector tool, there's a link to the floor planner, which is more of a diagram influence instead of just numbers and data that you get out. So it's helpful just for people to either show or try to figure out different simulations or positions of your memory interfaces.
But we don't have that tool support for Agilex M series yet. It just have Agilex FI series information right now, and it's yeah, in Stratix 10. Yeah.
All right. Well, I think there's no more questions in the chat, so I think we will call it a day. Just a few things to finish up here. So I've posted all the links that were on the slides in the chat, and if you're using Teams, you can always get back into that to get to those links. And I've also posted a feedback survey link. We'd greatly appreciate it if you would click on that and give us your feedback on this session. Our Ask an Expert sessions are monthly. We're actually we're a little behind. We're going to have two sessions this month to make up for the fact we didn't have one in August. So there will be another session later on this month. For registering and attending, you will receive an email at some point this week that will also contain the survey link in case you miss it, as well as a link to the recording of this session. So you can view that at any time. With that, then, I want to thank our experts, Bhumika and Damaris. Thank you all for attending, and we will see you at the next one. We're going to stop the recording shortly, and the Teams meeting will close as well. Thank you, everybody.
Thank you, Steve. Have a nice day.
Thank you.
Everyone.